Welcome to G Fun Facts Online. Today, we're delving into the world of a silent and patient predator, a creature that embodies immense power, the python. While its ability to swallow prey as large as an alligator is legendary, the true marvel isn't the swallow, but what happens next. Deep inside the snake, a biological furnace ignites, a digestive process so powerful it can dissolve flesh, organs, and even solid bone. For centuries, this was just a bizarre fact of nature. But now, scientists are looking into the python's gut with a revolutionary goal: to steal its secrets for the advancement of human medicine. This isn't science fiction. We're talking about a living blueprint for solving some of our most stubborn medical problems. Imagine treatments for bone-wasting diseases like osteoporosis, inspired by the very process a python uses to digest a skeleton. Or new enzyme therapies that could dissolve deadly blood clots, all derived from the potent chemical cocktail in a snake's stomach. This is the cutting edge of biomimicry, where we look to nature's most extreme and successful designs to inspire human innovation. So today we explore the serpent's superpower and how its incredible digestive system is unlocking a new frontier in medicine. The life of a python is one of extreme feast and famine. As a sit-and-wait predator, it might go months without a single meal. During these long fasts, its body is a masterclass in energy conservation. Its entire gastrointestinal tract shuts down into a near-dormant state. The stomach stops producing acid, the intestines shrink, and its metabolism slows to a crawl. But the moment prey is consumed, this calm is shattered. The snake might swallow a meal that equals more than half its own body mass, and this act triggers one of the most dramatic transformations in the entire animal kingdom. It's not a gentle awakening, it's an explosive, system-wide event. Within just 24 to 48 hours, the snake's organs begin to grow at an astonishing rate. This is called organ hypertrophy. The heart, liver, pancreas, kidneys, and especially the small intestine can all increase in mass, some doubling in size. The heart, for example, grows by up to 40%. It does this not by creating new cells, but by making its existing muscle cells bigger. This is crucial to pump enough blood to fuel the immense energy cost of digestion. And what's truly remarkable is that this process is completely reversible. Once digestion is over, the organs shrink back to their fasting size, ready for the next meal. This rapid organ growth is matched by a spectacular surge in metabolism. The energy a python spends on digestion, known as the specific dynamic action, is the largest ever recorded among vertebrates. Its oxygen consumption can skyrocket by over 40-fold. This is a massive energetic undertaking. To put it in perspective, imagine your own metabolism suddenly increasing by 4,000%. To fuel this, the python's body mobilizes enormous energy reserves. The concentration of fats or triglycerides in its blood can increase by more than 150 times, turning its blood into a milky, lipid-rich fuel source. The snake operates on a pay-before-pumping principle. It has to burn a huge amount of its own stored energy just to get the digestive engine started, long before it can absorb any nutrients from its meal. Now, let's get to the centerpiece of this biological furnace, the python's stomach. During fasting, its stomach is a neutral environment, with a pH around 7.5, similar to pure water. But within 24 hours of eating, specialized cells in the stomach lining go into hyperdrive, pumping out massive quantities of hydrochloric acid. This flood of acid causes the stomach's pH to plummet from a neutral 7 to a highly acidic 2, eventually reaching a searingly low pH of 1.5. That's more acidic than the battery acid in your car. This extreme acidity is maintained for days, and it's the first step in breaking down the prey. It denatures proteins, and, critically, it begins to dissolve the hard, mineralized structure of bone. X-ray studies of digesting pythons are incredible to see. They show the skeleton of a rat, completely intact on day 1. By day 6, it has completely dissolved and passed into the small intestine. But it's not just acid. The stomach cells also release a powerful enzyme called pepsin. This enzyme is a protease, meaning it specializes in breaking down proteins. The combination of extreme acid and powerful pepsin starts the systematic liquefaction of everything, soft tissue and skeleton alike. As this partially digested acidic slurry, now called chyme, moves from the stomach into the small intestine, another amazing transition occurs. The pH is rapidly neutralized, jumping from as low as 2.5 to 6.5 within just a few centimeters. This is likely thanks to bicarbonate secreted from the pancreas, and it's essential to protect the intestinal walls from the harsh acid. The small intestine, which has already doubled in size, becomes a hive of activity. Its internal surface area expands dramatically. The finger-like projections called villi get longer, but even more impressively, the microscopic projections on those cells, the microvilli, increase in length by 5 times. This creates an enormous surface area for absorbing nutrients. The pancreas then releases its own cocktail of enzymes into the intestine: trypsin to continue digesting proteins, amylase for carbohydrates, and lipase for fats. The activity of these enzymes skyrockets, ensuring the meal is broken down into its fundamental building blocks: amino acids, glucose, and fatty acids, which are then absorbed by the supercharged intestinal lining. This whole symphony is meticulously controlled by a rush of hormones. For example, a peptide called cholecystokinin, or CCK, can increase by 25-fold after a meal, coordinating the gut, pancreas, and other organs to handle the massive nutrient load. For a long time, the biggest mystery was the bone-dissolving part. The powerful acid was clearly a factor, but the process just seemed too efficient to be explained by acid alone. More importantly, how did the python absorb all the calcium from a large skeleton without it becoming toxic? Flooding the bloodstream with that much calcium would be deadly. The breakthrough came with the discovery of a previously unknown type of cell in the intestines of Burmese pythons. A skeleton is a rich source of minerals, especially calcium and phosphorus. But absorbing it all would be fatal. Researchers found that these pythons have specialized, narrow cells in their intestinal lining that are uniquely adapted to this problem. These cells contain a small pocket or crypt. As the dissolved bone moves through the intestine, these crypts fill up with tiny particles made of calcium, phosphorus, and iron. These particles are not seen in snakes fed a boneless diet, confirming they are a direct result of bone digestion. Essentially, these specialized cells actively capture the excess calcium and phosphorus liberated from the bones. They package these minerals into solid particles, which are then not absorbed into the bloodstream. Instead, they pass through the digestive tract and are expelled with the waste. This is an ingenious mechanism. It allows the python to get the best of both worlds. It can fully dissolve the skeleton to extract the minerals it needs, while simultaneously preventing a toxic overdose by safely packaging and excreting the excess. This discovery didn't just solve a biological puzzle. It revealed how an organism can evolve highly specific cellular machinery to handle extreme dietary challenges. And it is this precise system of bone deconstruction and mineral management that holds such tantalizing promise for medical science. This brings us to the exciting field of biomimicry, where we look to nature for inspiration to solve human problems. The python's digestive system, with its extreme adaptations, is a goldmine of ideas, especially for treating bone diseases. Let's consider osteoporosis. This is a debilitating disease where bone density is lost, making bones weak and prone to breaking. It's caused by an imbalance in our natural bone remodeling process. Specialized cells called osteoclasts are responsible for breaking down or resorbing old bone tissue, while cells called osteoblasts build new bone. In osteoporosis, the osteoclasts become overactive, breaking down bone faster than the osteoblasts can rebuild it. Now, here is the fascinating parallel. The way an osteoclast dissolves bone is remarkably similar to what happens in a python's stomach, just on a microscopic scale. An osteoclast attaches to the bone and creates a sealed-off microenvironment. Into this tiny space, it pumps protons to create an acidic environment that dissolves the bone mineral. It also secretes enzymes, most notably a powerful protease called cathepsin K, which digests the bone's organic matrix, which is mostly collagen. This is where the python's secret becomes medically relevant. The python system is optimized for the complete and rapid dissolution of bone. By studying the specific enzymes and the chemical environment it creates, researchers could develop better therapies for bone diseases. The goal isn't to dissolve our bones, of course, but to control the cells that do. For instance, understanding the python's potent proteases could inspire the design of highly specific inhibitors for that human enzyme, cathepsin K. The challenge with osteoporosis drugs is to slow down the overactive osteoclasts without stopping the essential process of bone remodeling entirely. The python gives us a model of extreme yet controlled bone deconstruction that could reveal new targets for drugs. The potent chemical cocktail in the python's gut has implications beyond bone disease. Its powerful proteolytic enzymes are master decomposers of tissue. This has scientists wondering if similar enzymes could be harnessed to break down other unwanted protein structures in the body. A prime example is thrombosis, the formation of life-threatening blood clots. Blood clots are mostly a mesh of a protein called fibrin. Our bodies have a natural system to break them down, but when it's overwhelmed, clots can block blood vessels, causing a heart attack or a stroke. Current treatments involve clot-busting drugs that try to activate our own clot-dissolving system. Interestingly, a rich source of powerful clot-dissolving enzymes has already been found in snakes, but in their venom, not their gut. Many snake venoms contain enzymes that can directly degrade fibrin, and some have been developed into drugs. The principle is the same, harnessing a snake's powerful biological tools for medicine. The digestive enzymes of the python represent another, largely untapped library of potentially therapeutic proteins that could inspire future drugs for everything from thrombosis to dissolving scar tissue, or even breaking down the protein matrix that protects cancerous tumors. There's one more major area of inspiration: drug delivery. One of the biggest challenges in medicine is designing pills that can survive the incredibly harsh environment of the human stomach. The low pH and digestive enzymes can easily destroy many drugs before they are absorbed. So how does a python's own digestive tract survive, being exposed to a pH of 1.5 and a barrage of its own powerful enzymes? Its cells have highly effective protective mechanisms. The intestinal lining is coated in a thick layer of mucus, and as we learned, the acidic chyme is rapidly neutralized as it enters the intestine. This has inspired researchers to create smart nanoparticles or capsules that mimic these defenses. The idea is to create a delivery system that can protect a drug from the stomach's acid bath and then release it at a specific target, like the small intestine. By studying the molecular structure of the python's gut lining and its protective mucus, researchers could design more robust and effective oral medications, transforming how we administer a whole range of medicines. The study of the python's digestive system is a powerful testament to the value of basic biological research. What started as curiosity about an animal's extreme biology is now pointing towards novel solutions for human health. This journey from a snake's gut to the forefront of medical science is a perfect example of the promise of biomimicry, a paradigm shift that views nature not just as something to be preserved, but as a vast, living library of brilliant ideas. The future of this research is likely to branch in several directions. The python will continue to be an invaluable model for studying fundamental processes like reversible organ growth and extreme metabolic regulation. The molecular pathways that control organ growth in pythons are also present in humans and are implicated in diseases like cancer and diabetes. Understanding how a python can turn these pathways on and off so precisely could give us critical insights into how they go wrong in human disease. Looking further ahead, we can expect more targeted efforts to translate these findings. This could involve using the structure of a python's digestive enzymes as a template to computationally design new synthetic drugs. We may also see the development of advanced drug delivery systems whose designs are directly inspired by the protective mechanisms of the python's gut. Ultimately, the python's secret is a reminder that the solutions to some of our most complex problems may be hidden in plain sight, within the extraordinary biology of the creatures with whom we share our planet. The ability to dissolve bone, once a mere biological oddity, has become a beacon of hope for medical innovation. By continuing to explore the natural world with a sense of wonder and a sharp scientific eye, we may find that the serpent holds the key to a whole host of medical miracles yet to be discovered. Thanks for tuning in to G Fun Facts Online.